Geometry people, if you do the Pythagorean theorem problems long enough and often enough, you'll start finding the same numbers keep appearing over and over, because there aren't that many numbers that will work evenly in the Pythagorean theorem. If three numbers work evenly in the Pythagorean theorem, we call them a Pythagorean triple. The most famous Pythagorean triple, or the most common one, let's not say famous, is 3, 4, 5. Well, 3 squared plus 4 squared does equal 5 squared. That's what makes it a Pythagorean triple if the numbers work. So this becomes 9 plus 16 equals 25, and yes, 25 does equal 25. Another one that works is 5, 12, 13. 5 squared plus 12 squared equals 13 squared. 25 plus 144 equals 169. Well, 25 plus 144 does equal 169. I'm telling you about Pythagorean triples because you start seeing the same numbers over and over, and after a while, if you see a 5 and a 12, you know the hypotenuse is going to be 13. So it can kind of save you the work of doing the Pythagorean theorem problem. If it's not a triple, you still have to do all the work. But if it is a triple and you remember it, you can simply say the answer. Now the thing about the triples is, if you start with 3, 4, 5, and you times every number by 2, that's called a multiple. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. That is also a triple. If you take the original triple and multiply it by a number, that will also be a triple. 36 plus 64 does equal 100. That's a triple. Let's take 3, 4, 5 and times it by 3. You get 9, 12, 15 is a triple. Let's do a couple more. Times it by 4. You get 12, 16, 20. That's a triple. And what I mean by this, if I give you a problem and the legs are 12 and 16, and you recognize that that is a multiple of the 3, 4, 5 triple, you can just say 20. Let's do one more. 3, 4, 5 times 5 is 15, 20, 25. If you start recognizing these numbers, it does help you do these problems a little quicker. And let's do the 5, 12, 13 one. Times it by 2, you get 10, 24, 26. Times it by 3, you get 15, 36, 39. Those are triples. You may not recognize them as easily as the 3, 4, 5, but the 5, 12, 13 triple you probably will recognize. And I'll just show you an example of how you can use triples to do these types of problems. Okay? We have a triangle. It's a right triangle. The triangle is called triangle ABC. I would write this triangle ABC with the capital letters. The little ABCs are the sides. And notice where I put the little a between the B and C. That represents the sides. And just the convention of how we do it, little a is opposite capital A, little b is opposite capital B, and little c is opposite capital C. Okay, so if I say A is 3 and B is 4, well, those are the legs, 3 and 4. Well, you could do 3 squared plus 4 squared equals C squared. But if you remember what I just showed you, that 3, 4, 5 is a triple, you can just say, C is 5. Okay? One leg is 5, the other leg we don't know, the hypotenuse is 13. Well, if you remember 5, 12, 13, you can just put a 12 right there. There's your answer. Okay, one leg is 3, the other leg is 5. Now, you may be tempted, some people, to put a 4 here because you know that 3, 4, 5 is a triple. But the 3, 4, 5 triple only will work if 3 and 4 are the legs. Here's the 5 is the leg. So here you can't use a triple. You would actually have to do the work. 3 squared plus 5 squared equals c squared. 9 plus 25 equals c squared. 34 equals c squared. And you get the square root of 34 equals c. And that can't be simplified because there are no perfect squares that go into 34. Oh, let's do one more. 10, 24, and c. Is that a triple? It kind of seems like it may be. There you go, 10, 24, 26. This is 26. Now, I'm not saying you have to use triples, but if you recognize them, you certainly can. If you want to work it out the long way all the time, you're more than welcome to. Now, before we close this lesson, I want to show you one more thing with radicals, and this will come up in your assignment. What if I gave you a problem where I said something like a is 2, b is square root of 10, and find c, right? Well, you would have to do 2 squared plus the square root of 10 squared equals c squared. You get 4 plus, well, what's the square root of 10? Well, the simple way to do that is if you think that squaring and square rooting are opposites, if you do the square root of 10 and you square it, you're just going to get 10. And you get 14 is c squared, square root of 14 equals c. Okay? I'll just show you a little bit of the work on how that happens. If you do square root of 10 and you square it, that means square root of 10 times square root of 10, and that means square root of 100, and well, we know that is 10. I mean, you can go through all those steps if you want, but just realize that squaring and square rooting are opposite operations. They kind of cancel out, and you just get 10. What if I gave you this problem? A is 3, b is 2 times square root of 5. Let's find c. Well, it would be 3 squared plus 2 square root of 5 squared equals c squared, 9. Now, how would you do this one? This exponent of 2 applies to the 2 and the square root of 5 both. If you apply it to the 2, 2 squared is 4, and we're going to multiply that. If you apply it to the radical 5, well, we just learned square root of 5 squared is 5, and you end up getting 9 plus 20. 2 square root of 5 squared equals 20. And you can do that on your calculator if you wish. 29 is c squared. Square root of 29 is c. Cannot be simplified. Okay? So I hope that Pythagorean triples might help you do your Pythagorean theorem problems. You don't have to use them, but they are a tool if you want to use them.